We've got Nicolas Durrande from Monumo.
Thank you, Rich. Hi, everybody. We started the day with electric motors, and we're going to end the day with electric motors too. Maybe one fun fact that I learned after joining Monumo is they actually consume, like electric motors in general, actually consume 50% of the electricity worldwide. So if you can improve motors a little bit, and of course there are lots of different types of motors, but that can make a big difference. And electric motors or generator also generate 95% of the electricity worldwide, except for solar panel. Everything basically turns a turbine, and we get electricity from there. So yeah, it's a very interesting area to be in with possibly big impacts. One caveat from the talk is I'm not going to talk about uncertainty at all, but I can promise you some Gaussian processes at some point. So hopefully I will do. So what I'm going to present is a joint work with colleagues at Shift Lab, Jonathan, Chris, Rupert, Marcel, and Lisa. And so I'm going to talk in general about electric motor design, some freeform parameterization of motors, and some machine learning surrogates to approximate numerical solvers. So designing electric motor, in one sense, can be seen as just one optimization problem. So you will have multiple objectives. You want typically to maximize the efficiency of the motor while reducing the cost of material or the mass of the machine. There will be lots of constraints on different things about the mechanical safety, about the torque you generate, about the power you need to get this torque. And so all the constraints add one to another, and there are a couple of objectives. And the design space can be quite small. Maybe there's like 5 parameters you want to tweak, but maybe there are like a few thousand parameters because you have a lot of degrees of freedom in the way you represent your motor, the object you want to optimize. And in order to know if a motor is good or bad, we use, in 99.9% of the cases, numerical simulations using finite element solvers, and in 1% of the cases, some test bed that will run, and we make sure that we are happy with the correspondence between what we simulated and what we actually measured. Interestingly, when you talk to engineers, they are quite comfortable with a 10% to 20% difference between the simulation and what they actually measure on the test bed. If you get 2 different teams to do 2 different measures on the test bed, they will also have a huge discrepancy. Even if you go to the same manufacturer and you ask for the same element twice, there will be some variabilities. There's a lot of discrepancy. Just a numerical simulator is the best we can get, so we're working based on that. So you need numerical simulations for electromagnetism, so to compute how much torque you get, what are the losses in your motor. For mechanicals, when you spin your motor at top speed, what's the stress in it? Does it break, or is there some fatigue? And for thermal properties of the motor. And all in one, when you have a candidate design you want to evaluate, this should be roughly like 100 finite element analysis simulations. So roughly 10 minutes on just one CPU. And then you need to parallelize that because you want to evaluate lots of designs to find a good one. By the way, do interrupt me anytime if you have a question during the talk. I'm happy to take them. So the classic approach, in order to make this difficult problem tractable, is first of all to focus on a small number of variables. So maybe you'll have 15 variables you want to optimize for your motor, and you forget about the other ones because you do that in several stages. You don't really look at the problem from a system-level perspective. You will have some people optimizing the motor, they're optimizing the inverters, another one optimizing the gearbox, and then they will have specifications to talk to each other. And in the end, they want the system globally to perform well, but it will be evaluated component-wise. They try not to simulate all the physics at once, so maybe they won't do mechanical simulations too much, but they will have some constraints about the minimal bridge thickness you have in your steel in your motor, because if it's too thin, you're going to have more stress in there. And the state of the art is to use genetic algorithm like NSGA2, and maybe with a few tens of thousands, maybe 100,000 simulations. So what we're trying to do at Monumo is we want to increase the dimension of the design space to do more system-level optimization, so optimize jointly the inverter and the motor. So maybe your motor will be a bit worse, but you will save on the inverter. And also you can get more intricate geometry, so you're not limited by the few parameters you have larger search space and possibly better solutions in there. But to do this, you need a scalable finite element solver so that you can have a larger evaluation budget. Making it scalable just means not paying licenses to ANSYS, pretty much. Like these licenses are expensive, so you can't get too many, even the high performance compute license. So having our own solver makes a big difference. And then we try to follow a bit more of a data-centric approach and less of just a classic optimization algorithm. Okay, the first part of the talk will be about how to increase the degrees of freedom when we design the motor, how to get more intricate geometries. So on the left, you have like a classic design. So this is a quarter of the motor. You have the shaft in the center. The rotor is this part that's a bit that spins, and the stator with the copper windings in these slots. The current pass through the copper, generates some electromagnetic field that interacts with the magnet, and you get the motor to rotate. But these designs will have a few degrees of freedom. So you choose the number of magnets you have, their size, their angles. The air pockets here have a few parameters too, what's their size, and these sort of things. So you have a template with some degrees of freedom that gives you a view of the design space, in a sense. And what I'm going to talk about is a bit of crazier design. This design is a very bad design compared to this one. But where you have lots of degrees of freedom, you don't have to specify the number of magnets you have, like all number of magnets are in the design space. The air pockets can have intricate shapes. They can be separated from the others. So it's not exactly topology optimization, because what I'm going to present, you cannot really make appear air pockets or magnets. Like it's more gradient descent based on those representation of the motor. So the challenge is you want to have a parameterization of the motor that is expressive enough so that you can make good designs out of it, but you don't want to have too many nonsensical designs either. So on one extreme of the spectrum, you have a templated designs with, say, 5 degrees of freedom. On the other extreme, you have a lot of degrees of freedom, and for each pixel, you choose which material you have here, but is like pretty much none of the design space here will make sense. So you want to have some structure, you still want to have some regularity, but still having lots of degrees of freedom. And there's a very good friend of mine to encode regularity and smoothness, and that's Gaussian processes. So I'm going to use Gaussian processes to have freeform designs, but inject some regularity into them. And I'll start with a simple example where there's no magnet. So it's just steel or air in your motor. This is the X and Y axis on these plots are pretty much like the same X and Y axis on this one, and only representing the rotor, so the green parts on this plot. But basically, I can take a Gaussian processes that is defined over R squared, and I can sample these Gaussian processes to generate a smooth function, and then I can threshold this function to decide what material I have in what places. And in here, if the value is positive, if the value of the GP is positive, then I end up with air, and when the value of the GP is negative, I end up with steel. So that's one way for me to get lots of degrees of freedom, but still to retain some smoothness in the boundaries between material. So in practice, in order to generate those samples, I start by picking a set of control points that cover the rotor. In the previous graph, they were the vertices of the mesh. Then I can compute the mean function of the GP at these locations and the covariance matrix at the locations of the control points. Then I compute a square root of the covariance matrix. And in order to generate a random sample, so a random geometry, I can just take a mean vector plus L times some Gaussian white noise. And that gives me the sample I was plotting before. This is to generate random samples. In practice, I want to parameterize a motor with some degrees of freedom. So the only thing I need to change in here is not to sample the epsilon, but to parameterize this epsilon. In here, the epsilon are defined on R for each of them. I'd rather have a design space that is an hypercube. So I'm making X defined on 0, 1 at the power n, and I'm just mapping it through the inverse CDF of the standard Gaussian. And that gives me something that if I sample X uniformly on 0, 1, I end up with the Gaussian process as an output. I can also expose these parameters to an optimizer in order to get geometries and start optimizing over X. So one thing I didn't discuss previously is the choice of these square roots I'm using. So typically people would use like a Cholesky decomposition of the covariance matrix in order to get samples. There's one that is a bit more relevant in our case. It's taking the square root from the eigen decomposition of the covariance matrix. If I write, yeah, I don't really understand. There's no, yeah. All right. PDP transpose, this gives me basically P D1/2 here. It can be seen as a square root of the covariance matrix. So if I multiply this by the white noise or by my parameters mapped through the inverse CDF, I do end up with some samples that have the distribution I'm interested in. The interesting thing here is these matrices that contain on diagonal the eigenvalues, the eigenvalue will decay quite quickly, and pretty much like the higher frequency variations you get in P, in the eigenfunctions, the smaller the eigenvalue is going to be. So in a sense, the Gaussian process comes with a basis of functions with increasing frequency, but also decreasing amplitude. So that's a very nice way, even if I end up with lots of designs variable, because I have, I think, like 450 nodes on this graph. It means I have 450 basis functions to combine in order to get a function out there. But I have a nice ordering of them. So if I just want to pick the 20 largest, for example, but I know I should just look at the 20 large eigenfunctions with the largest eigenvalues. So this is very much like principal component analysis, just done for Gaussian processes that is sampled in some locations. So yeah, the Gaussian processes comes with a nice basis. So let's look at some points in our design space, and those are machines that are sampled like uniformly on my unique cube as a design space. It has some of the quantities that we are interested in. The boundaries between materials are smooth, but there are a lot of issues with this one. On the first picture, for example, the steel is not connected to the shaft, right? So like that's not even a motor. There's no way you can transmit torque for this one. Another problem we have is the fact that there is a symmetry in the motor which says like the material on this boundary should be the same as the material on this boundary, because to recreate everything over the 2π circle, then you basically replicate periodically this shape. So here I have problems with the boundary conditions. I may have some like floating pieces of steel, which is also a problem. And I don't have magnets in here, and magnets are helpful to get torque. So let's address those one by one. So first of all, we want to ensure that we have steel in contact with the shaft. So in order to have steel, it basically says that you want your Gaussian processes at these locations to take negative values. So that's an inequality constraint, that's a constraint on a continuum of points. So like these two things make it difficult to encode exactly with Gaussian processes, but there's a very short sweet shortcut, which is for the points on the control points that are in here, I'm just going to impose a negative value. So I'm going to impose the value of -1. It's a bit arbitrary, but it does what I want. I end up with steel at the interface with the rotor, so I know I can transfer torque. So Gaussian processes are convenient here because there's a closed form formula for the conditioning that I can use and impose a material somewhere in space where I'm interested to have a specific material. The problem, actually, it can be seen here. The second problem we had was the fact that the lower angular boundary was different to the upper angular boundary. So I don't have smoothness in here. Typically, if you don't have smoothness, you end up with stress that concentrates in the mechanical simulation. So we want to get rid of that. Basically, we want some periodicity, angular periodicity here. And there's a good way to do that with Gaussian processes is to take a periodic covariance function. A nice way to see that in this specific case is to say if this is my rotor in 2D, I can embed this 2D into 3D and end up with a cone. So I'm basically stitching these two boundaries somewhere here, and I have a classic covariance function that sits over a 3D space. I'm only evaluating it on a 2D space, so I have in a sense like a flat cone that represents these flat surfaces, but I don't need to do anything tricky, just I expose coordinates that are embedded into this 3D space, and when I compute the covariance function, the covariance between these 2 points is going to be the covariance between these 2 points, and it's going to have a correlation of 1. So second good properties of Gaussian processes. And the third problem we had was the floating pieces of steel. That's not something you can easily guarantee with the Gaussian processes. Continuity over a long range of things. But there is one thing that is pretty straightforward that we can do and that can help, is just change the mean function of the Gaussian processes. We remember we had a threshold of 0, and we were saying this is air, and this is this one here is steel. I could either change the threshold, but in practice it is nicer to just shift the covariance of the Gaussian processes to bias towards one material or another. So if I had a negative mu, I will make the value of the Gaussian processes smaller. I will have more steel. If I make the value positive, I will have more air into the rotor. So with very large values of very small values of mu, it's pretty much all steel, and I'm sure there won't be floating pieces of steel with high probability. Okay, and issue number 4 is adding magnets. So far we're just thresholding a function that was giving us one material or the other. But what happens if we want to have more material? We could try something with like more thresholding, saying if it's above 1, it's a material. If it's between 0 and 1, it's another. If it's below 0, it's yet another material. But then you would have things with 2 materials that can't touch each other, for example. So a nicer way to look at things is to consider a latent space for materials. So we'll use an embedding space that in this case is going to be 2-dimensional, and to each material I'll assign a vector into this space. I'll call this vector the representer because in a sense like it captures, it represents one material in the latent space. So the directions here are arbitrary, they are just 3 directions, one for each vector. The second step is instead of sampling one Gaussian processes, scalar valued Gaussian processes, I sample a vector valued Gaussian processes. So for each of the nodes, for each of the control points, I have a little vector that has a direction. And then I can look at for a given node. I think I have air, steel, magnets, and for a given node, let's take this one over here. I have one vector that is like that, and to decide which material is assigned to this node, I'll basically take the inner product between f at xi with the 3 representers, and I'm going to assign the material that is the closest according to the inner product. So that gives me a nice way to assign as many materials as I want. Like if I have 4 materials, maybe I'd be tempted to take a 3D embedding space and not a 2D embedding space. You could also pretty much like see those as one hot encoding, just like projected on the diagonal of the plane, orthogonal to the diagonal of the cube. But that's a way that, in a sense, you can cast the 1D problem I was talking before as this. It was just before we had 0, and we're saying if you're positive, you have air. If you're negative, you you have steel. It's just the generalization with one more material, one more dimension. Yeah. Okay, and in the end, we end up with this representation. In yellow, you have air. In blue, you have steel, and in red, you have magnets. For magnet, we also need to decide what's the magnetization direction. I'm doing that with another quotient processes that is vector valued, and I just average over these areas what's the direction of the arrows, and that gives me the magnetization direction. So all in one, this is like a pretty high-dimensional representation of my motor with lots of degrees of freedom, but still some regularity. And I have, I think, around 2,000 degrees of freedom for this, but with a very nice ordering of them because of this structure I started with in the first place. I tried some experiments where I truncated the bases to pick the 50 most important ones, the 200 most important, or all of them, and I found that there's no downside of using all of them. So maybe the optimizer sees some degrees of freedom that don't have much effect, but you can cope with it pretty well. Okay, so now we're all done. Like we have a design space that has like most of the properties we care about. So we can do some simulation and some optimization into this space. So the second bit of the talk is about using these freeform designs and doing some predictions based on them, using machine learning models. From a high level, the simulation pipeline can be represented like this. We start with some parameters, so those will be the 2,000 freeform parameters I was talking about. The pre-processing I just described gives us a machine object for which we can do some simulations. We get some fields. So for IMAG, it will be the B field is possibly the most important one. And then from this field, we do some post-processing to compute all the losses. So what are the losses in the steel, in the magnets, and all the losses you can imagine. So it's quite tempting when we see this. Say, oh, there are some input parameters, there are some output values. I'm just going to fit an end-to-end machine learning model that will take the inputs and map that directly to the metrics I care about. We tried that. It doesn't work very well. The problem is it's very difficult to collect some data that is both balanced and that is also diverse. So if you use, to collect the data, some random sampling, so you just sample some random motors, but none of them will be very good motors in the end. And all your metrics are going to be quite poor, and maybe out of 1 million motors that you sample uniformly in the space, none of them will satisfy the constraints. On the other hand, if you use an optimization algorithm to collect data, so to bias the data collection toward good designs, it will take like quite some time for the optimizer to reach the feasible region, and in the end, you don't have that much diversity into your training sets. So what we did was a combination of these two things. We generated a couple million random samples. We ran maybe 20, 30 optimizations in parallel in order to get a data set that tries to have a good coverage of the space, but also bias towards the regions of interest. And then if you look at all the performance metrics independently, you can get models that are pretty accurate. So for example, you want, from an IMAG perspective, you want a model to have sufficient torque. So label 1 means you have enough torque, label 0 means you don't have enough torque. But out of the 30,000 data points, maybe there's 1,000 that are not predicted well. For the torque ripple, which is around 1 rotation, if you consider a full rotation of the motor, how much does the torque vary? You want the torque to be as consistent, as flat as possible, not to get too much variations in the motor. But again, most of the points are well classified, and then if you look at the convergent metrics for voltage, it's even better. So independently, when we look at the 3 models, they look all right. But if you combine the predictions of the 3 models, you end up with an overall classifier that is very poor. So first of all, there's a huge data imbalance because pretty much none of the data points in the test set actually satisfy the constraints, and then like the error is now quite large. Like when you predict that a value is true, you have a 50% chance to miss it, and it's even worse in the other direction. What happens here, and what I'm trying to show in this picture, is that the objectives we're looking at, they're like very highly correlated. Maybe another like more schematic but easier to understand way to represent that is to look at the torque versus voltage. I'm doing here. There are negative coefficients in there, so I'm going to do this way: torque versus the voltage you need in your simulation. And basically, the more torque you get, the more voltage you've put in with your inverter. So these points are going to be very highly correlated. And the good design is a design that will have a large torque for a small voltage. So it's only this portion of the designs that are valid designs, and everything else either violates the torque constraints or violates the voltage constraints. But the fact there is some like strong correlations between these outputs means that they are very difficult to predict, and even a model that is, in a sense, good at predicting are you above the torque constraints or are you above the voltage constraints, when you combine them, they are capture pretty poorly what's happening there. So the direction we took was not to try to fit an end-to-end machine learning models, but try to just emulate the finite element solvers, just to replace this core bit of the simulation. The pre-processing is something like it's kind of all code, we know how to do that. This is also something we can re-implement with like an auto differentiation library. But the difficult part is this one. Can we replace the finite element solvers with machine learning models? And the idea is to have them as like drop-in replacements, so take the same inputs and produce the same outputs. So let's rapidly talk about the physics, just because I need some of these concepts on the line. So we have a 2D magnetostatic problem. If you look at the two Maxwell equations we care about, this one, the fact that B is divergence free, can be guaranteed just by working with the magnetic vector potential A. So we say B is the curl of A, and A is not the quantity we are going to solve for. So we end up with just one equation, and since we are just in 2D, the first two components of A and J are going to be zero, and we end up with this equation. And J will capture how much current you're putting into the coils, and the magnet will also, this derivation is without magnet, but in practice, if I were to add magnet, they would appear on the right-hand side here. So let's solve for A, the magnetic vector potential. So the modeling task is we want models that will operate on mesh or graphs. So this will be the type of input. We have a mesher, we use Gmesh, that will mesh or freeform geometry. You'll see different materials. I don't know which one is which, but in the rotor, the stator is fixed in our experiments. And from there, you want to directly predict the values of the magnetic vector potential. The benefit here is there's no concept of data imbalance at this point. You're trying to learn the physics, so even if the model is very bad, it will still be informative about how the physics behave. We have the same granularity as the finite element solvers, so it can easily be compared or replaced in the simulation pipeline. We will get gradients, which we don't have with our solvers at the moment, so we're experimenting with doing some like gradient descent on these mesh objects. And potentially, it's a simpler task, because what we really want to do is just to learn the solution of something that is quite compact in a sense. The output we want to predict is A, and from A we can derive the other quantities we care about, including the B field, the magnetic flux density, which is just the curl of A that the model will predict. So from the model architecture, which is a transformer architecture with 10 layers, it's pretty much an out-of-the-box model. We didn't make much changes to it. The input features will be all the vertices of this graph. We ignore the edges at that point. So we want their location, both in polar and Cartesian coordinate. The material, what's the material present in the vicinity of the vertex? What's the polarization around the vertex, and what's the current captured by the vertex 2. And the output features is A is the main one, that's really the one predicted with ML, and then analytically from A to B. This picture on the right is the amount of steel at vertices. So you will see like vertices that have a large neighborhood, they have more steel in a sense in these locations, and the one that have a small neighborhood, so maybe around here, just have less steel. So regarding the model accuracy, the model can be pretty accurate. On the left-hand side, you have the predictions of the GNN of the transformer model, and on the right-hand side, you have the error. The thing to notice here is the order of magnitude difference between these values. Another way to look at the error is to, for one given mesh, plot the error at each vertices. So all these points are obtained just for one mesh, and we find a very good alignment. This specific mesh is the median of the validation set. So that's like a representative example. And yeah, and if you look at the entire validation set, then we end up with like an R square that has 2-3 lines, depending if you look at the mean or the median, and more critically, no outlier. There are, sorry you can't see it, there are a few values, like maybe there are 10-ish values over here that disappeared when I exported the plot, but the worst part we have is still above 0.9. So the models can be super accurate for A. Then from A, we derive B. So that's the predictions we obtain from the GNN on the left, and on the right-hand side, it is the error. It's not exactly the error on B; it's the error on B times the cell area. Since we use, in a sense, finite difference to compute the curl of A, on small cells, you can have very large error, even if your model on A is pretty accurate. But it's not too much of a problem in our case because it's a large error that pretty much comes from a 0 divided by 0. So if we just multiply B by the area of the cell, which is the quantity that is needed down the line for computing our matrix of interest, then this error disappears, this large error disappears. So yeah, there are some, maybe not in this example, but sometimes we have some degenerate cells that are extremely thin, and this can lead to large errors when we do the numerical computation of the curve. So it is not as good as A, which is a bit expected, like there's a differentiation step from going from A to D, but it's still satisfactory. And this is the model accuracy we get for the B field. The metrics are a bit less good, but still very satisfactory. We're happy with those. And a few concluding remarks. So the ML models can accurately approximate the FEM solvers. It is for a lower cost. We measured 2x to 20x speed up. It's basically 20x when you make the model, the ML models run on GPU, and 2x if you make the ML models run on CPU. I'm not sure, maybe the 2x comparison is more fair because the solver itself we're comparing to runs on GPU, and CPUs are, sorry, the solver runs on CPU, and GPU are more expensive. But we didn't try at all at this point to make the models faster by quantization or reducing the number of layers or whatever. It's just, can we get accurate models? And the answer is yes. Another interesting thing to us was that small data sets are enough to learn the physics. The model I'm showing here have been trained on a bit less than 100,000 simulations, which is not that much. Maybe that's not the right way of looking at the problem, because in a sense the PDE we're discretizing has a meaning at the vertex level. So maybe we should count the number of vertex. One vertex as a data point and not one graph as a data point. And if you do that, then all of a sudden it's a larger data set. You have 600 million data points in vertices in the data set. So maybe this would be this number, which corresponds to the number of tokens that are used to train the model. and this is the number of simulations that are required. And we've put a lot of things, a lot of message passing, neural networks, some transformer, visual transformers, a lot of things, but like, every time there was a transformer in the name of the architecture, it basically worked better. So that's our go-to tool when we are facing new problems now. There's still open questions. This is a work in progress. We didn't yet check how much this solved the data imbalance problem, but I really believe that since the physics is implemented in every regime, like these models, expecting them to perform better. And now that we have gradients, we can do interesting things with those gradients into the optimization of the motors themselves. Okay. Thank you very much.
Thank you, Nicolas. Questions, please.
I'd like to ask, how much improvement did you get over the motor designs compared with traditional methods?
Sorry, say it again.
How much improvement in the motors that were designed using this did you get compared with traditional methods?
Okay.
And also, what did the engineers think of the designs?
So the issues I highlighted in the first place, they come from the engineer when we show them the designs in the first place. They were saying, this doesn't make sense, this doesn't make sense. So we're back to the parameterization to make the design space capture these things. Regarding do they perform better, there's still some things that we don't catch up with. For example, the numerical simulations actual motor designer would use would have will be pretty smart at the interface between the magnets and the steel. So we'll either have like a model for glue or frictionless contact, and it's something we completely neglect in here. So we fused everything, so they won't trust our numerical simulations either. So I don't have a definite answer, but those are that much better. Yeah, it's part of the thing. Like we want to push that and actually now use the gradient descent from the gradient information we have in order to do some optimization. I still think that doing genetic algorithms in super high dimension isn't that great. Like the crossover and mutation operation don't make that much sense. So I'm more after the gradient information than I am after the actual accuracy. So yeah, sorry, I don't have a good answer, but hopefully soon.
With the back, yeah.
Just wondering about the mixture between the random and the optimization-based approach for acquiring.
Yeah.
Can you share more information?
Yeah. So we basically started with just the random designs and generated a few millions, and then realized that the data imbalance was there were just a handful of feasible designs in all of those. So there was no chance to train classifiers in this space. Then we biased the data collection by using optimizers. So again, genetic algorithms that we let run for a few days, and we did that 20 times. Now we could see like some cluster of points, like there were like interesting plots to show you can't look at what happened in the 2000 dimensional space, but you can look at in the objective space that is lower dimensional, and we could see some like clusters in some area and more scattered around in others. So there was some improvement in the balance of data, and I think we got to a few % of feasible designs with this approach. But then the diversity was quite small because these genetic algorithms, even if they are multi-objective, they tend to narrow down to some solution, some area of a small portion of the design space. Like they don't keep covering the entire Pareto front. So it was a bit better, but it was kind of like not enough because the model we had in the end were not good.
But couldn't you kind of have another model that is a classifier for valid designs?
At which
like
overall
constraints.
So yeah, the confusion tables I was showing were these kind of classifiers that we're trying to predict either per objective or globally.
No, for the additional problem that you had, that you have invalid combinations, so that the actual simulator is not the geometry that is it's not sensible. Right?
It's not the invalid geometries. We have very few of those in the end. It's more not satisfying the constraints.
Okay. Do you have a question, Sinead?
Yeah, I think this maybe is a combination of the open work and what you just said about genetic algorithms, but when you're using your Gaussian process parameterized model with this loss, do you know how close to convex your optimization solution is?
Yeah, so by running multiple optimizations, I end up in different locations of the design space. So it's really
just
not,
try a few times.
really not convex. I'm just hoping that the kind of hierarchy there are between the variables is something that will help the optimizers. But yeah, it's just wishful thinking. Yeah.
Great. Let's thank Nicolas again.